Now, like we can hello again. Now we are prepared for the next presenter for the next session today. The first presenter, sorry, first speaker, Monica Powell.
Okay. Thank you. First of all, thank you to the organizer for giving me this opportunity to present my work. Today, I will talking about state space of a compact quantum group. It is a joint work with Professor Ishan Patri and Dr. Mulay Mondal. And this presentation is divided into four sections. Initially, I give some motivations, and then I recall some definitions. Then I will talking about the probability measures on a compact group, and finally I will talking about the state space of compact quantum groups. So in 1955, J. Wendell provided the necessary and sufficient conditions for a regular probability measure to be invertible. More precisely, he proved that a regular probability measure on a compact group is invertible if and only if it is a point mass. And next, he also proved that there is a one-on correspondence between the idempotent probability measures and the compact subgroup of a compact group. Now, we in this presentation we generalize the first result for arbitrary compact quantum group. That is the main result in these presentations, and for the second results in 1996, Arup Pal provided a counter example by showing that these results cannot be generalized for the arbitrary compact quantum groups. Now, next, J. Wendell also proved that for any closed normal subgroup, the compact group G, thus, first of all, if we have a compact group G and normal subgroup H, we have another compact group G by H. And the set of regular probability measure of this quotient group for this quotient group form a semi-group. And Wendell proved that this semi-group is basically isomorphic to the semi-group S of CG star H compose pi, where H of H is the hard measure corresponding of the closed subgroup H, and pi is the surjective star homomorphism from CG to CG by H. Here CG means the set of all regular probability measure can be think as or the set of all continuous function from G to C. C means the complex number. So throughout my presentation, I will generalize the first result and the last result of these three results. So for this, we recall some definitions. Throughout this presentation, we denote this one to denote the minimal tensor product of sister algebra. Now, what compact quantum group means? Compact quantum group is a unital sister algebra together with a unital star homomorphism delta from CG to CG tensor CG called as co-multiplications satisfying these two properties. One of these is co-associatives and another one is co-cancellation law. If these two conditions are satisfied for a unital sister algebra, and we have we have a co-multiplication, then we can say that compact this unital sister algebra is as a compact quantum group. For example, if we take a compact group G and consider the set of all continuous map from the compact group G to the complex numbers, we find that this set is this ring, but this sister algebra form a compact quantum groups. Next, we're talking about the state. State means a positive linear functional phi from a CQG. We just, for clarity and gravity, we denote CQG as a, for a compact quantum group as a CQG. So state means a positive linear functional phi on a CQG CG with norm 1. We denote the set of all states on a CQG G as a S of CG. Now, a special type of state, that is co-unit, is a star homomorphism satisfying these conditions. That means a state if satisfies this which is a star homomorphism and satisfies these conditions, we can say that this is a co-unit. Next, whenever when we consider a compact quantum group and we consider all the states of that compact quantum group, we find that the set of all these sets form a compact monoid with respect to the convolution product. That means for any two state phi and psi, phi star psi equals to phi tensor product psi compose delta. And with respect to Weierstrass topology, we find that this set form a compact monoid. My motto is to characterize all the Green's relations or for this semigroup. Okay, so for this we introduce the Green's relations. As we already discussed only monoid structure, so we restrict ourselves for the monoid. In a monoid is the Green's relation script L, R, script R, script J, H, and script D on this monoid S are defined as for any two element AB, A script related to B, if and only if the principal left ideal containing A and principal left ideal generated by B are coincides. Similarly, we define other Green's relations. These five relations are equivalence relations. So here in this presentation, we characterize for this characterize Green's relation for this monoid. So initially we try to discuss for the compact groups. So we know that there is a one-on correspondence between the regular probability measure and the set of all continuous mapping from CG2, that means the set of all continuous mappings G to C to C. So in 1975, J1 proved that for any compact group G and closed subgroup H, the maximal subgroup containing first of all, whenever we have a compact group G and phi of H, then we have another state phi of H. That means phi H is H of H compose pi. Pi is this one, and this phi H is form a state. And now, whenever we have this compact group J1 characterize the maximal subgroup containing this state. Basically, this state is form a idempotent state. So he characterized a total maximal subgroup as the maximal subgroup containing the idempotent state phi H is the set of all elements of the form delta x star phi H, where x belongs to NH, where NH is the normalizer of the subgroup H in G. And we prove that that means this maximal subgroup is nothing but it is a script H class containing this idempotent state. And we prove the other Green's equivalence classes containing this idempotent state. As if we have a closed normal subgroup H of G, we find that all the Green's equivalence classes are the same, and that is equals to delta x star phi H, where x belongs to G. Next, we generalize these results. For this, we consider a compact group G and a compact subgroup H. And we find that the Green's equivalence classes containing phi H as follows. That means script L of phi H is the set of all elements of the form delta x star phi H, where x belongs to G. Similarly, we can characterize or evaluate all the other Green's equivalence classes containing this idempotent state. Next, we talking about the arbitrary compact quantum groups. For this, we use these two results. First result states that if A is a unital sister algebra and U equals to Uij is a unitary matrix in MNA, such that A is generated as a sister algebra by Uij, and suppose T is a unital completely positive map from A into some sister algebra B, such that the matrix T of Uij in M and B is also unitary matrix. If this condition happens, then we can prove that T is a star homomorphism. Now you also use another result. The linear span of matrix coefficient of finite dimensional representation of a CQG is dense in CG. Using this result, we obtain this main results of this presentation. That means for a compact quantum group CG, the invertible element in a S of CG, this semigroup, is a character. Basically, it is easy to prove that any character is is form a invertible element of this semigroup, but converse was still remains difficult little bit. So here I prove this one. For this, we consider a pseudomatric matrix compact group CG, that is unitary crystal generated by this matrix coefficients of this unitary matrix, and we consider a invertible state phi. Since it is an invertible state, so it has a inverse psi, and that means phi star psi equals to epsilon. This is a co-unit, and that is equals to psi star phi. And using uij, we got two matrix, phi of uij and psi of uij, and their product is identity matrix. Since phi and psi are states, so norm of this matrix lesser equals to 1, and therefore it is a unitary matrix. And using the previous lemma, we can say that phi is a character. And finally using the previous propositions and the multiplicative domain argument, we can say that every invertible state is a character for a arbitrary compact quantum group. Next, we characterize for the other. That means for whenever we consider the compact group, we already characterize any idempotent state. That means J. Wendell proved that if any idempotent probability measure correspond to a compact subgroup, so it is easy to characterize all the Green's equivalence classes containing that idempotent probability measure. But for the arbitrary case, there is no similar notions. That's already proved by Orupal in 1996. We characterize for the arbitrary case this one for site for any normal compact quantum subgroup H of G, the following equations are holds. That means we find that all the Green's equivalence classes of the idempotent containing the idempotent state phi H is basically chi compose E of G quotient H, where chi is a character of G quotient H. That means actually it is a conditional expectation from G to G by H. Whenever we have a compact quantum subgroup, we have a normal compact quantum subgroup, we get another compact quantum subgroup G by H, and E is the conditional expectation from CG to G by H. Now we find that another result, that is a generalization of the J. Wendell, one of the results J. Wendell's, that is if H is a normal compact quantum subgroup of a compact quantum group G, we find that this semigroup S of C G cosine G by H is isomorphic to this semigroup S of CG star phi of H. This is a generalization of the third result of J. Wendell. This is the references. Thank you.
Thank you so much, Monica, for the nice presentation. Now,